Hi, I am Alireza Abbasimoshaei from IMEC Institute from Hamburg University of Technology. Today I want to talk about our new finger rehabilitation system and our paper titled by Developing and Control of a Novel Finger Rehabilitation Mechanism. Due to demographic change and the aging of population, diseases such as strokes are expected to increase over the years. In this situation, the medical sector is reaching its capacity limits, making any solution that takes over time intensive treatments that can be standardized. In this paper, a mechanism for finger rehabilitation therapy is presented. After identifying the requirements, a detailed investigation of the current situation and rehabilitation devices is presented. A working prototype for fingers is designed and built to show the capacity of the mechanism. It can be operated independently and is adaptable to different finger sizes. The prototype consists of a linear microdrive connected to the finger mechanism via Bowden cables. Additive manufacturing was mainly used as the production method. The prototype was successfully tested on 4 people with hands of different sizes. It allowed an actuation of 85 to 110 degrees for all joints. Different settings of the Bowden cable allow the actuation of different sections of the finger. Different settings of the mechanism, actuator, control analysis, and optimization are presented. As I said in previous slide, demographic change and aging population make a lot of problems. And the traditional method has a slow progress rate. So it requires constant presence of a physiotherapist, which needs a lot of time and is very cost intensive. So patients can become frustrated or even depressed and disengage with the therapy work. So our objective is the need for a system that enables the patient to conduct therapy independently. So we developed an exoskeleton finger rehabilitation system. And the benefits of that is patient can train easier and they can do medical sectors by themselves and they will get control back from other people. Also they can compare their progress with other people, and also family member can make more motivation for people. So the goal is patients invest more time into the therapy and stays engaged longer. According to Yu et al., devices are classified into 3 categories: mechanical linkage, cable controlled, and pneumatic or hydraulic mechanisms. Mechanical linkage systems use a direct connection between an energy source such as a motor or actuator and an effector, which is connected to the fingertip or joint, as you can see here. Cable-driven mechanisms for rehabilitation devices can be subdivided based on the use of cables or Bowden cables. As the name suggests, the Bowden cable relies on the pulling of the cables to generate torque for the joints. The movement of the Bowden cables is not as precise as that of the cable pull, as it is not under constant tension. For devices with a high number of degrees of freedom, Bowden cable mechanisms are used because they have a lower demand for actuators and cables. Hydraulic or pneumatic mechanisms with pneumatic power transmission are not common in rehabilitation or research applications. A disadvantage of the hydraulic approach is that handling a fluid in a medical environment can cause hygiene problems. At best, it is water, or worst, oil, but this always increases maintenance. Also, vibrotactile is a very useful idea for rehabilitation, but the use of different tactile systems makes the system expensive and difficult to control. So the main aim of this system is to propose a simple system that can be used alongside other vibrotactile systems. By analyzing of previous systems, we analyzed requirements for physical therapy necessities. The system should have the ability to train each joint. Also, the system should be more than just a depiction of performed movement. So it should move different fingers with different speeds or in different ranges. So to achieve that, we used the system with haptic feedback also with force feedback. By analyzing the previous systems, we showed you some findings and learnings. So the objective is following a path. So the learning is to find an efficient way to measure success. Many different movements trained, but rarely with a source. So by analyzing the requirements, we used a system for physical therapy which are necessary. Not all previous systems record movement data. So the important features should be diagnosed and recorded. Not all systems offer support and resistance. So the learning is include both for highest possible usabilities. And most of previous systems did not provide each joint movement. We aim to provide the maximum degrees of freedom with the least number of motors. As you can see, this is the general structure of the desired device. So we send the electricity to battery and then to motor. Also, we have a control unit that will be send signal to motor. And motor will move mechanism, and the mechanism will provide the extension, flexion, movement of each joint. Then we have a feedback loop, and an observer will send the signal to setting, and then setting will send signal to control. So the mechanism should be less than 1.5 kilogram, and it should provide the needed angles for each degrees of freedom. And the operating time is better to be less than 1 second. So it means that when patient moves the potentiometer, it should send the signal, and motor should move the finger or any joints, and this process should be less than 1 second. Now, to find the best mechanism, we need to check the anatomy of finger. So as you can see in the picture, the fingers of the human hand have 3 joints: MCP, PIP, and DIP. They are all hinge joints that allow 1 degree of freedom. Also, we have thumb, and the thumb is an exception. as the MCP is positioned at the wrist and thus represent 2 degrees of freedom. So now the approach is based on literature review, and after weighing the advantages and disadvantages of the approaches mentioned in the introduction, the decision was made in favor of cable control mechanisms. They can have the potential of additive manufacturing for efficient design at a low cost, while the solid and durable steel cable provides the power transmission. This was preferred because the surface quality and durability of the additive manufacturing parts could not be guaranteed. The Bowden cable can perform movements in both directions and requires only one drive, one fixation point, and one guide for flexion and extension of the finger. This advantage over cable mechanisms leads to the decision to use the Bowden cable. Since this work develops a mechanism that can be used for all kinds of devices, a versatile applicability should be ensured. In this step, 2 different design approaches were considered and tested. The problems of the first design were analyzed and a new approach for the second design was developed. The problem of unnatural movement of the fingers was solved by moving the mechanism to the back of the finger and passes the attachments through the side space only. The 2 cables on each side of the finger and their guides were combined in a bridge on the top of the finger. On the back of the hand, the base board is mounted, to which the first segment of the mechanism is attached. This segment is identical to the most distal segment. The adjustable length for different finger sizes is solved by dividing the middle part of the mechanism, which lies on the first finger segment. Looking at the prototype for different fingers shows the principles that can be adapted to form a complete hand rehabilitation device. The mechanism is designed to be modular to fit all fingers, but the connections and details to build the whole devices are not addressed. Nevertheless, a possible solution for the different mechanical situations on the thumb was considered. To make the thumb suitable for different uses, a rotation axis was added to the extension plate to allow different thumb positions for maximum applicability. The Bowden cable mechanism has already been identified as a practical way to transmit the force of the actuator and transfer the torque to the joint. Initially, a twisted steel cable with a diameter of 0.8 mm was chosen for the system, but it turned out that this size was too thin to transmit the force. A small resistance on the mechanism resulted in a bend before the first segment. After increasing the diameter to 1.5 mm, which could not be bent to a required radius, the perfect size of 1 mm was found. The tab at the end of the cable is connected to a pin or a screw on the linear actuator and moves through the holes in the segments of the mechanism. Additive manufacturing is used as the crucial production technology. Better known as 3D printing, additive manufacturing enables new possibility in engineering and design. As the name of the process suggests, an objective is made by joining materials together. Then we use the drive units. To operate the stiff Bowden cable, it was decided to use a linear actuator. This allows a precise movement and defines the actuation of cable. The Bowden cable does not bend around an axis of rotation, thus preventing frictional forces and deformation. After a complete research and a market comparison, the Octonix microlinear actuators proved to be the best choice to meet the requirements. In this system, the LAC board automatically reduces the input voltage from 12 volts to 3.3. The control is done by a potentiometer, as you can see here, and the voltage will be defined and will be sent to the motors. Then the measurements were taken to determine the actual speed at the different angles. Then we went to controlling the system. To ensure safe rehabilitation, such a positioning system needs adequate speed control. For this purpose, 3 control approaches were analyzed with Simulink, presented in the following section and ordered according to their complexity. In this study, 3 different variants of the Simulink models were analyzed. The 3 variants are ordered according to their complexity. The first is a simple model of a unidirectional system. The second variant allows changing the direction and the type of movement. And the third one is the final, complete simulation that includes noise and disturbances, as you can see here. So the system has noises, and also the desired speed will be defined, and a PID controller is used to control the system. To test and analyze the behavior of the system with these external influences, one must consider the third variant of the model. As you can see here, we showed you the second and third variants, and these are the control parameters and resetting time. And these 2 graphs will show the outcome of the system, the input desired speed and the output speed. Then, as a conclusion, in this work, a mechanism was developed to allow external actuation of fingers. A prototype was made using additive manufacturing and connected to a structure that allows testing. It consists of a mechanism with 2 Bowden cables connected to a linear actuator with a stroke of 50 mm. This actuator is controlled by a circuit board that allows the adjustment of stroke length, speed, and accuracy. Also, a potentiometer was wired to the board to operate the actuator with the previously set and positions. The mechanism represents a way to implement hand rehabilitation into everyday life. It can actuate the paralyzed fingers also and support the rehabilitation process. It can be operated in a mobile way and allows the patient to use it independently. The mechanism can support physiotherapists to provide quick and available rehabilitation when medical facilities reach their capacity limits. The mechanism is designed to fit all fingers. The variation of the middle segment by 6 mm to adjust its length according to different hands, which provide that for all applications. It focuses on wide applicability and to bring that as a cost-effective system. So normally rehabilitation devices with less functionality are in the range of 5,000 euros. But in this system, taking into consideration of all marginal costs and labor costs, different things, the maximum of this product will be 1,000, and the bill of materials is just 480 euros. These are the references. Thank you for your time.